Lovely. Okay, welcome all of you for a second time this semester. My name is Zach Brumbach. I'm one of the TAs for this class. Basic introduction stuff. As I said last time, PhD student here in electrical engineering, teaching this class for a while and blah, 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 whatever. Okay. Yeah, so you guys have a second exam on Wednesday. And I'm here just to answer questions. We'll go through everything as much as we can. If you ask me like, well, can you go over this section exactly? I don't know the numbers that the sections are. So if you could tell me, like, instead of go over 2.4, maybe talk about what onto is or something like that, just for clarity. But yeah, we can go and get started. So what questions do we have? And if at any point there are any questions, I'll probably just start explaining stuff or pull up a question that I think relevant or hard. So if you want, you can email me questions for files, because that's how I upload in my iPad, or you can just ask and I can put it on there pretty quickly as well. So questions can be as broad as what the hell is a span or a column space to what is the answer to this problem on this homework or the answer to this problem on this quiz. So yeah. Can I talk about subspaces? Absolutely. So for this exam, the big thing that you guys have learned at this point, hold on, I hear some echoing, so I'm just gonna make sure my computer volume is off. That's my iPad volume, that's what it was. Okay, so it's not gonna let me mute myself, that's fine. Okay, subspaces. Oh, yes, sorry, I got lost in the middle of my train of thought. There are a few new things for this exam, right? Your big ones are column space, null space, onto one-to-one subspaces. I think that covers the gist of it, and I believe 2x2 determinants are on there as well. 2x2 inverses, sorry. Can anybody correct me on that? Is that correct? Okay, that's just off the top of my head, so I hope that's correct. But if not, we'll cross that bridge when we get there. So first, let's talk about subspaces. Okay, why do we talk about subspaces? Why do we care? Anybody have any idea why we care about these things for this class? Not rhetorical, I promise. Okay, so there are two big subspaces we care about. This is kind of the motivation of why we talk about it. And those two subspaces are the column space of A and the null space of A. Okay, this is why we talk about subspaces and the properties that define them. And then we kind of ask some other things that could be subspaces or anything along those lines. Okay, so to be a subspace, three qualifications need to be met. And what we call those three qualifications together is we call it being linear. So as you can imagine for this class, being linear algebra, being linear is something that's pretty important. And there are three things that make a subspace. Okay, number one, it contains the zero vector. I'm just going to say it contains zero, okay? And in parentheses, 0 equals 0. So if you plug 0 into the condition and it is true, then that passes that qualification, okay? The next two kind of go hand in hand. Number two is closed under addition. And number three is closed under scalar multiplication. And what scalar is it means we're multiplying by a number, okay? We're not multiplying by variables, we're not squaring, we're not doing logarithms, we're not doing anything like that, okay? It's like multiplying by 4 times 10 times negative pi times anything like that, okay? And any combination of these are totally fine within subspaces, okay? That's the whole idea, is we do these three things and we stay in that space, okay? So you can think for column space, right? Column space always contains the origin, right? Whatever span you have, it'll always contain the point 0. Likewise, you can add vectors in your span and it'll stay in your span, or your column space. Or if you multiply by any vector within your column space, you do still stay within your column space, okay? Those are the big three ideas for column space, and the same is true for null space, okay? This is true for null space. Why is it not true for solution set? Because the solution set where B isn't 0 or something that's not the null space is translated. It's that plus BP that we talked about, right? Plus the particular solution. So if it's a solution set to something where B isn't equal to 0, it is not a subspace, actually. It's a translated subspace, translated null space. Okay. So let's talk about what these three things mean. Okay, the 0 one, pretty straightforward, kind of easy to tell like that. Okay. What closed under addition means, I'll just rewrite 2 here. What it means is if U and V are in the space, then U plus V must also be in the space. A very good example we'll see where something does not pass this qualification, okay, would be is if I give you X, Y, Z, and I ask you to make sure that X times Y times Z is equal to 0. Okay, that's your condition to make a subspace. Okay. So for something to be a subspace, it must, all three of those conditions must be true. So, for example, if we plug in all zeros, is this condition true? Yes, right? So the first one would be true. For closed under addition, something you would have to think about is pick a U and a V such that each of them multiply to be 0, but when you add them, we try to get it so that they're not. Okay. So being X times Y times Z equals 0, what does that mean particularly? A little louder.
One of them is equal to 0.
One of them is equal to 0, right? Right? That is either X 0, Y 0, or Z 0, not exclusive. 2 of them could be 0, 3 of them could be 0. Okay. I'll explain it like this, and then this is actually a homework question, I believe. So I'll also show a nice little graph of it real quick. But so what we need U and V to be, okay, is we need someone give me some U where one of the entries or 2 or 3 of the entries are 0. 1 0 0 is a great answer. 1 0 0. Okay. So now, what we're looking for this not to be closed under addition is a second V that matches this condition that when we add them together, it no longer holds true. Okay. So what that means is we're looking for a V that has a 0, that when we add it to this, no entry is 0. Okay. Can somebody give me an example of that? 0 1 1, right? Because is U in the space? Yes. Is V in the space? Yes. What is U plus V? Equal to 1 1 1. Is 1 1 1 in this space? No. So this is an example of something not being closed under addition. Okay. Each of its separate pieces are in here, but it is not when we add them together. Okay. So this isn't something you necessarily need to understand the next time I'm going to say it, but it helps some people see it in a geometric sense. Okay. So what I'm going to do for this same question is I'm going to plot what the solutions look like in 3D. Okay. So if X has to equal 0, Y has to equal 0, or Z has to equal 0. Okay. That creates the X, Y, Y, Z, and X, Z planes. Okay. It looks like this. Here's this plane, here's this plane, and here's this flat plane. Okay. Maybe I should pull up an easier way to show this. Water. Come on. Y equals 0. Z equals 0. Okay. So now we look at this. I'm sorry for those of you who are watching online, but it is just this graph, but a little bit prettier than I can draw. You see here we have these 3 individual planes that form this weird looking space, right? And what this means for like closed under addition is we can pick any 2 things on here, and if you add them together, they still have to be on here. Okay. So for example, we pick something that goes on this plane here, and it goes on this plane over here. We add them together, it's out here in the middle of this space, right? And it's no longer on any of those planes. That's what it geometrically means to not be closed under addition. Does that make sense? Any questions on this? If there are any questions at any point, feel free to also interrupt me. Yeah, or just raise your hand at any point. You know, this is, if you have that question, someone else has that question too. And I promise I've heard a stupider question than any of you could come up with, I hope, in terms of this class at least. But that's, again, geometric approach for this. Okay, just kind of thinking of what the space actually looks like. All right. So now back to here. Now there's one more condition, and that is being closed under multiplication. scalar multiplication particularly, okay? What that means, if you have a space and you have any vector or any combination of x, y, z, or x1, x2, x3, x4, x5, whatever, and you add it to another one that also satisfies the condition, okay? They should both satisfy the condition still. An example of this would be, for example, if I give you x and y, such that x plus y is less than or equal to 1, okay? So what this looks like, I'm going to draw it on a graph just to do everything at once. It looks something like this, I think. So, as you can pretty much see here, as you can see here pretty easily, right? If I pick a vector that is just like this, okay, where I pick x equals 1, y equals 0, okay, or 1, 0, right? Does this satisfy this condition?
Yeah.
Yes, right? What happens if I multiply it by 10? Does it still satisfy the condition? No, right? Because if I have, I'll call it in general, just x and y times c, which is some number, okay, that's scalar multiplication, picking some c. This gives us c times x plus y less than or equal to 1, okay? C can change whether or not this is true, all right? Oh, that's not right. It's more expanded like this, but who cares? Something along those lines. That's not incredibly important. It's more of the idea. Okay, so can we see here that like if this x is 1 and this y is 0, and multiply it by like 3, it's no longer true, right? Any questions on this? So usually what they'll ask is they'll ask a counterexample, or they'll just ask whether or not it is. So an example would be for not being closed under multiplication, c equals 10, and then I'll just call vector equals 1, 0. Something along those lines, okay? Any other questions on subspaces? Does that hopefully answer your questions? Your question? Okay, what else we got? Yes. Oh, okay, yeah. Yeah, go for it.
So what does necessarily mean that like a span of space?
Okay. So the question was, what does it mean when someone says that a span is a subspace and a subspace is a span? That's not exactly true, actually. So the way I like to think about it is every square is a rectangle, not every rectangle is a square, right? Every span that contains the origin is a subspace. It doesn't contain the origin, it's not. Okay. So every column space or null space will always be a subspace, but not every subspace can be necessarily defined as a column space. Okay. Does that make sense? Okay. It's kind of like a broad picture of things. Like here's column space, null space, and here's everything else. Okay. So that's why we give you equations and stuff. Another little trick is if they ask you, if they give you x, y, and z that satisfy the condition x plus y equals z. Is this a subspace? Without doing any math, is this a subspace? Why? Does anyone have a definitive answer that they're confident about? To what? This is your system. Kind of. The way I like to think about this is how can we rewrite this? Well, we can rewrite this as x minus y, x plus y minus z equals 0. And what is this? It's a null space, right? Is a null space a subspace? Yes. We don't have to do any math. It can just be done there, okay? Good rules of thumb is if you see like a +1, okay, not a subspace. If you see like an x times y, not a subspace. Probably. You do have to check these, but that should be your intuition, okay? Especially for this one, because it'll fail automatically when you plug in 0. An example of where that would fail, x, y, z, such that x plus 1, such that it gives us a vector x plus 1, y plus z, z plus 2x. What happens when we plug in the 0 vector? We plug in x, y, and z to all be 0, and what vector do we get? Is that 0 vector? No, so it fails that condition, so it's not a subspace. Okay. Any other questions on subspace before we get going? Yeah.
So both of the examples you gave.
Yep.
Kind of focus on one of the two conditions.
Yeah.
If like, for example, for closed-ended addition, if we have that example, how do you make sure that the multiplication, like, can we just assume that multiplication is taken care of and already satisfied?
No, just because one condition is true or false doesn't tell you anything about the others. So for this example here, actually, if I pick some C times some vector that is in the space, okay? Some vector is in the space, we said X or Y or Z is equal to 0, right? So we say X, Y, Z is equal to 0, right? So when we multiply CX, CY, and CZ, this gives us C cubed X, Y, Z equals 0. Does it matter what C is for this? Given that X, Y, Z is equal to 0? No, right? That's why we pick our vectors for closed-ended multiplication and addition such that we start with things that are true, okay? So in this case, this is 0, so whatever C is, never not going to be 0. Does that make sense? Yeah. So just because you know one is not true, that tells you it's not a subspace. It does not tell you anything about the other conditions, okay? So it's kind of based on the question they give you. They ask, is this a subspace? A little bit quicker, if you can find a counterexample. They ask you each part, you have to go through each thing individually. Okay. All right. What else? Yes. Yeah, last example. Oh, how did I know that this is a null space? The easy answer is because it's an equation that doesn't have any numbers in it. Okay. And I reordered it so that it looked like this, which is the same as rewriting this as 1, 1, -1 times our X vector equals 0. Okay. So if you can get an equation like this, that's a null space, right? That's the definition. Okay. Yeah.
What do you think of the variables?
It depends on the context, which is not a very satisfying answer. Should you think about the variables as columns? If you can put it in a matrix, yes. But if it's X times Y, you can't put that in a matrix, can you? Or absolute value of X times Y plus 1 or something like that, right? Does that kind of make? This is an example where you can't usually use matrices. Okay, so you kind of, this is the algebra part of linear algebra with the linear part with no matrices for some reason. Okay. There won't be anything like this for the rest of the class, I promise. Any other questions on this? Oh, nope. Okay. Okay, moving on. Yeah. Can I explain range? Yes, I absolutely can. So I'm going to go through this talking about domain, codomain, range, null space, and column space all at the same time. Okay, because they all tie together in a very nice way, that with a nice diagram that I like to frequently draw. Okay. If you've watched any of my past videos, you're going to see this diagram in there as well. I like it. I think it's intuitive. I think that it shows that where everything is appropriately. Okay. So just as a little side note before we get started, column space of A is just equal to the span of the columns of A, which we talked about before this exam. We're just rewording something we use for exam 1. Null space of A is equal to the solution set to AX equals 0, right? So that's just new terms for things we've already learned, right? And one other thing I'll say, you still need to know the shape of each of these, okay? What is the shape of my column space? It's R to the number of pivots in R to the number of rows. And I put quotes around the first part because that's not technically true. It's technically just this dimensional space, okay? For the second one, what is the shape of a null space? It's R to the number of free variables in R to the number of columns, okay? So we're going to learn a new term, and we're just going to say range is equal to our column span, our column space, okay? But they kind of talk about different things. We talk about range as more of like the images or just different terms for the same shit. I don't know why they do it, but they do. So let's look at it on a graph. So I like to draw my lovely engineering potatoes. If you are a mechanical engineer, you'll see a lot. They're just like space to space, or how you translate things or anything like that. Okay. So I'm going to write this as This is the space where I wrote y, that's not a y. This space on the left, we call our domain. Okay, it's where we start, okay? It's our input stuff. And we always input x's, okay? So this is where all of my x's are. Every x vector that exists is in this little bean-shaped thing, okay? And the shape is equal to r to the number of columns. Okay. And what's going to happen is we're going to take each point in x and we're going to shoot it through A. Okay. And what A is A is essentially a length. Okay. It's what I'm doing in my transformation. You can also call this your T of x. Okay. It's the same thing. Right. So we're going to go through A and it's going to reflect us somewhere and we're going to hit some place in our codomain. Okay. And this one's shape is equal to r, the number of rows. This is all of our possible b's, okay? So if we have 5 rows, this is R5. If we have 2 rows, this is R2, okay? And all of our different x's that shoot through here are going to make some kind of space, okay? And it's going to look something like this. Okay, it can be anywhere, it can be any shape, it can look like anything. It can fill the whole space, it doesn't have to fill the whole space, okay? And these are all of our b's we can reach, or all of our b's that are consistent, okay? And we call this a range. And its shape is r to the number of pivots, right? Because remember, we call this column space of A. It's the same thing, okay? It's just for all of my b's, everywhere in this space, they go somewhere to one of these b's, okay? Does this make sense as an overarching example of just where these 3 things lie in the relationship? Are there any questions on this? Yeah. It does. Okay, so just because we have all these different x's doesn't mean that they go to unique places necessarily, okay? We could have one spot right here, okay? And we could have a whole bunch of different x's all plot to that exact same thing when they go through A, okay? I overshot it. Okay, so all these different things all get plotted to the exact same x, okay? I'm going to erase these. Okay. Within our column space, what point has to be contained always? 0 vector, right? Cool. So our null space is all of the x's that get us there, right? I'm gonna write this in green. So say this is the trivial solution. Makes sense. We put 0 in, we get 0 out. Absolutely nothing happens. It passes through the lens like it's nothing. Okay, it goes right through the middle, well, however you want to think about it, okay? But if we have a null space, there are other x's that give us solutions to ax equals 0, right? And what these things make is they make a smaller shape here. This is our null space. Okay? So everything in this blob all goes through A and gets mapped to the 0 vector, okay? Likewise, for every other point in the column space, so for every other point, let's call this some generic B, okay, that has a set of solutions. There will be, pick a different color. Interesting. Okay. So curious. Oh no. I'm going to close that door. That's actually going to bother me. I'm going to get distracted. UCCs, I have no idea what that is, but apparently they like hairstyles, I guess. So if we're going to a different point B, all of our solutions will make another shape. Okay, and all of these things say go to this different B that was here. Yes, I will start that over. Yes. So if we choose a different point over here, B, all right? And so what I'm looking for is all the x's that get us there, okay? So say like this one, we go through here and it gets us to this point B, okay? And there'll be a whole bunch of them, okay? This is if we have a free variable, we have infinite solutions, right? What happens is what this is This is a translated null space. This is exactly the same shape as the null space, shifted plus VP, plus a particular solution, okay? We're moving everything in here by an amount of a particular solution, okay? So every point that exists over here in this column space, in our range, every single point has a blob over here that is exactly the same shape as the null space, okay? And whatever that blob is, all of those things, when they go through here, magnify to just that one point, okay? We call those the solutions, okay? Whatever value B, whatever value 0. However, the reason we talk about the null space is because it's the only one over here that contains a 0 vector. Okay, that's why we care about it. It's a subspace. Everything shifted is not. Okay. Does that make sense? Yeah. Hmm? Yeah, that is, if we only have the trivial solution, okay, this isn't a blob, this is just a point. And then just the point goes through there and goes there. Every other point goes through a different spot. Okay. Does that make sense? How does that happen? You can kind of think about it as if here, right, we have this whole space that goes here. That's dependent on our A, that's dependent on how we're shaping things, okay? If we shape it differently, maybe this whole thing goes to different places, right? So we pick some A that instead of shifting all this to one place, it shifts all these to different places, okay? Does that make sense? So when there's not a blob and there's only a point, it just goes to the same. Okay. The big things you need to take from this are the domain, and the codomain, and the range. Okay. Yeah.
I have a point inside the null space.
What? Oh, that's just the 0 vector. Okay, that's just me showing that the null space is the only one that contains the 0 vector. That's the origin. Okay, that's just me showing where that is. Okay. Yeah. I absolutely can. I'm going to ask if there are any other questions. That's exactly what. Any other questions on this? Yeah. About to get there. You have another question about onto 101? Or okay.
The basis.
A basis is basically like your fundamental building blocks with absolutely no redundancy. Okay. I'll draw a little diagram on the side. Actually, remind me after I talk about onto and 101 to keep this track, and then we'll go into that. Because that will definitely be on your exam. That will be at least one, maybe two of the questions. You find a basis for this. Okay. So let's talk about what this means in terms of onto and 1-to-1. Okay. So for onto and 1-to-1. Okay, these are dual things of each other, all right? They kind of build in opposite ways that kind of come together into another term that you just learned, I believe, earlier. Okay, so onto means every B has at least one solution. Okay? Every B is at least one solution. What does it mean for consistency? If every B has at least one solution. It's consistent for all B. This upside down A means for all. Just in math speak, if you ever see this, upside down A means for all. If you see this backwards E, that means one, or there exists particularly. Usually singular, can be multiple, but that's usually how it is. Consistent for all B. So what does that mean for my range? Particularly how it's related to my codomain. It's the same size. Range equals codomain. Okay. So how many pivots do we have? Well, looking back at this, the codomain has the shape of R the number of rows. So if we're onto, how many pivots do we need? Pivot in every row. Exactly. We need a pivot in every row. Okay. So it's just a little sidebar here. There are three different shapes any matrix can take, right? It can be wide, it can be square, or it can be tall. Okay. For a wide matrix, can we have a pivot in every row? Yes. For a square matrix, can we have a pivot in every row? For a tall matrix, can we have a pivot in every row? No. Okay. So if they give you this tall matrix that's, I don't know, 15 by 3, you don't have to do any math, you know it's not onto it. That's the question they ask. Okay, you don't have to stretch yourself out about the row reduction. Okay. And I'll draw what this looks like. And what it looks like is we have all of A, or all, sorry, here's all of our X, here's our A's, and here's all of our B's. Okay. Let's say X is a little bigger. Let's draw it like that. Okay. I know this is a smaller diagram. But what onto means is all of these get cramped into here and every single one of them hits every B. Okay. So all of this goes to all of this. So range equals codomain. Any questions on onto? Okay. Does it make sense why this would be important? Like why we're looking at something? And if it has the qualification to get everywhere, it seems like something that's worthwhile to know, right? Because if we can get everywhere, everywhere has an X. Another way to write that, okay? Every B has an X. Every B is at least one solution, okay? One last note. We've accounted for the number of pivots, right? What does this tell us about the number of free variables? Nothing. Okay. So we don't care. We don't care anything about our pivots and our columns. We only care about our pivots and our rows. Okay. So going off of these things, all right. For one-to-one, onto had at least one solution. What do you think it's going to be for one-to-one? At most one solution, right? Every B has at most. Okay. So the last one talked about being consistent for all B. This one doesn't talk about that. It instead talks about each B has a unique X or is inconsistent. And just to go back and clarify for this diagram, okay? If this is my column space here, okay? For a B that's here, this is inconsistent, right? It's outside of my range. Kind of how you can see that in terms of consistent, right? What's outside of your range is inconsistent. It's not in your column space, okay? So, what does it tell us about range? Do we know how big it is? Yeah. Is that a question or an answer? Okay. Anyone have any thoughts on how big the range is going to be? Domain, exactly. You can think of this as now these two aren't the same size, and we're taking all of this and putting it inside of this space. Okay, that's what one-to-one means. Okay. Kind of how you can think of it spatially like that. Okay. I'll draw the diagram in a second as well. Questions so far? Okay, yeah.
So earlier when we were talking about like shape,
Yep.
R to the number of whatever,
Mhm.
or A and R to the whatever.
Yes.
How does is range the first one or the second one?
Range is the first one. Yeah, so we can rewrite column space up here. Shape, range in codomain. Okay, this is how we can rewrite that, what that looks like for columns. There's not a good reciprocal for null space. Okay, it's just in the domain somewhere, whatever shape it is. Okay. So, onto had a pivot in every row. So one-to-one is going to have a pivot in every. Yes. Column. Okay. So thinking about pivot in every column, talking about the three different types of matrices, three different shapes of matrices rather. Can something that's wide have a pivot in every column? No. Can something that's square? Can something that's tall What's the only case where we can have both? Square, okay? So if we know it's square, we don't know if it's onto or 1-to-1 just off the bat, okay? Or rather, if it's not onto or 1-to-1 off the bat. Yeah.
How does range put that in again?
How does range what?
Put that in.
Range equals domain because we have a pivot in every. I didn't get there yet, did I? Oh, I did. Pivot in every column. Yeah, we pivot in every column, right? So what my range looks like, right? It's going to be R to the number of columns in R to the number of rows. Okay, and our number of columns is just our domain, right? In codomain. Okay. It'll make a little bit more sense when I draw this, okay? So what this means. Okay, this is my domain A and codomain, okay? What 1-to-1 means is as I put all of my x's through here, okay, what it's going to make is it's going to make the exact same shape as my domain in my codomain. And each thing gets mapped to a very clear point, okay? You can think if I'm literally just taking this and placing it here. If I give you somewhere in here, can you tell where it was? Yeah, right. So the motivation here is that we can get each way to each solution in B for everywhere in our column space, okay? At most one solution, there's either one solution or 0. And since there's at most one, we know there's no repeat, right? If there's no repeats, we can trace this line right back to where it started. Okay. Likewise over here, we can have a lot of repeats. So if I give you some point, you go here, or you go here, or you go here, or wherever, right? We don't know necessarily. Okay. That's kind of the motivation between 1-to-1, onto and 1-to-1. Okay. So looking at these, right? We have to start in different size spaces for each of these conditions to be true. Okay. For this one, can my domain be bigger than my codomain? For onto, not 1-to-1. Yes, right? Think like you're trying to go from here to map all over this. You're trying to fill in this entire space. Okay. If this is a line and this is a plane, can you get everywhere? If this is a plane and this is a 3 space, can you get everywhere? This is a line and this is a 4 space. No, right? This needs to be at least as big as this to fill the whole area. Okay. So that's why it needs to be y a square. Okay. Because we start in columns, we end in rows. Okay. Yes. Yes, I'm about to get there. Okay, so here instead for 1-to-1, if each thing only has one place to go, we can't cram anything. Okay, it has to fit nicely in this space. Okay, so can this be bigger than this? No, because if it is too big, we have to smush it in, right? And then we have repeats. We have null space. Okay, we have null space. We have infinite many solutions for something. And that means that it's not 1-to-1. 1-to-1 means we have at most one solution, not infinitely many. Okay, so for this one, we cannot start in a bigger space. We can only start in a smaller space or an equally sized space. Okay, likewise over here, like I said, you can't start in a place that's smaller than where you end. Okay, does this make sense so far? I know there's a lot going on here in geometry and stuff that's kind of confusing in this context, but questions on this? Okay. So with this onto, we can tell we go everywhere. And with this, we can tell we can either get back or it doesn't have a solution. So when it has both, if it is both onto and 1-to-1, we call it invertible. Okay, because if something is invertible, it is both onto and 1-to-1. Okay, if it's onto, we can get everywhere. If it's 1-to-1, we can get back. Okay, so if we have both at least and at most one solution, how many solutions do we have? Exactly one. For all B. Okay, So if it's invertible, what this looks like, start here, we end here, go through A. Okay, what this looks like is each of these, while it might be kind of crooked, okay, doesn't necessarily need to be straight looking. Each place over here is going to have only one way back. It's 1 and 1. And everywhere in here is reached because it's onto. So every single point over here can be traced back to a point over here. Okay. So instead of going this way, we can also go this way. That's why we call it invertible. Okay. Any questions on onto 1 and 1 or invertible? Yeah. Yeah, so you said 1 to 1, right? So 1 to 1 having a pivot in every column, okay? What does a pivot in every column tell? I'm just going to say this out loud. This is too much, right? What does a pivot in every column tell you about the linearly independent nature of your columns? Every pivot is, every column is linearly independent, okay? So since every column, every vector that is a column is also linearly independent. Did I just say that in a circle? Kind of think so, but that's okay. Does that make sense? Does that answer your question? Okay. So yeah, for 1 to 1, another little bullet you can put down here. All your columns are linearly independent as well. Okay. All of these things go the same way. All right. If you are given something that has pivot in every column, all of these other things. If you're given the statement each b has a unique x or is inconsistent, you know it's 1 to 1 and all the other conditions are true. Okay. Same is true for onto. If you're given any of these other bullets, you go backwards like that. All right. And one last little note to make. What do we know about the number of free variables for something that's 1 to 1? There are none. There's a pivot in every column, no free variables. Okay. All right. Any other questions on this? Yeah. Yes, I'm good. Yeah, making sure there's no more questions on this, and then I'll move into that. Yes. Hmm? Yep. Each x can only ever have one y. Okay, right? That's the definition of function. But for each y having at most one x, that is 1 to 1. Okay. For each y having at least one x, that is onto. For each y having exactly one x, that is invertible. Okay. This is the time when you have both at least and at most, right? When those two intersect, then we call it invertible. Okay. Yeah. Can you say that again a little louder? Oh, yeah. So when we talk about like being unique for solutions, right? Each input will always have an output. Okay, that's not really something that we talk about at all. That's just kind of the progression, right? We start with x and it goes through there and it goes to 1. What we care more about is going the opposite direction. Okay, each b having only 1, or each b being able to trace back to multiple, or each b not being able to trace back at all. Okay, that's how our solutions are. These lines are solutions. Okay. That's the image is what this is. Translating from x to b. This is my image of this. Translated through a. So I kind of think of it as a lens that makes an image. Okay. Does that make sense? Okay. Any other questions on this? Yeah. If you could find the question and let me know when you've done that, and then we can go over it. Yes. Oh, you have the question. Okay, fantastic. What is it? Yeah, that'd be fine. Yep. Okay. So what this one asks is there's just an additional piece in here with onto and 1 to 1. And what it asks is a transformation. And the definition of a transformation is each x goes to some y. Okay, by t of x. Okay. It's just this weird question they like to throw in there. It's just saying transformation transforms x, right? Yes. I don't know why they asked it like that, but that they do. Is that the part of this that was the question, or was it the other two as well? Okay, I'll be hanging out a little bit after you have more questions about it. So, thank you. All right, so now moving into finding a basis. Okay. So you know how for the last one I drew this nice little diagram of how to find like your solution set and span. It's exactly the same diagram. Okay. We start with A. Okay, we don't have to be given a B because it'll be about column space or null space, so neither of them need a B. Okay. So if we're looking for a basis of column of A. Okay. Sorry. First step, what do you always do? Row reduce. Always, 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 always. Okay. When in doubt, if you're sitting in a question, have no idea what you're doing, just plug it in a matrix and row reduce. Okay. So basis of the column space of A. To find this, we take the reducer echelon form. We find pivot columns. Okay. So something to note is we find these columns and we note which ones they are. Say it's columns 1, 2, and 4, okay? Okay, so say I reduce, say I have a pivot in column 1, column 2, and column 4, okay? Then, I should keep this all on one page. Then from here, my basis is equal to, what is our pivot columns of original A, not reduced row echelon form. Okay. Because when you row reduce and you find your pivot columns, right, you'll have 3 things and they'll all be 1 zeros everywhere else. Okay. So you just know which ones they are in the reduced row echelon form, and you only take the pivots from the original matrix. Okay. An example. Okay. This matrix here, oh, that's on narrow. Spoiler alert, it row reduces to 1 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0. Okay. So if I'm given this matrix and asked to find a basis for the column space, first reduce row echelon form. Okay. Then I note this column, and this column have pivots. Therefore, my basis is 1 0 0 0, comma 0 2 3 4, and 0 0 0 1. Okay. This is these columns. We put it in reduced row echelon form to determine which columns they are. Okay. Then from here we backtrack to the start. Okay, this one is far less work than finding a basis for a null space. Okay, you only have to row reduce and be done. All right. Yeah.
Concerning like the notation, you just put it like that, or
Yeah, that's fine. You can just say the basis is whatever. It just, you can put the curly things, you cannot put the curly things. It really doesn't matter. Because all this means, it means a set. Okay, so saying the basis is these 3 vectors is the same as saying the set of these 3 vectors. Okay, we put the curly brackets particularly for like spans of things, right? But we're talking about 3 vectors, not the span of them. These are fundamental building blocks for what is the column space in this. Okay. Yeah. Nope, it'll ask you. Yeah, it'll be very explicit, like find a basis for this. Okay. Find a basis for the column space space, find a basis for the null space space. Or if they give you an equation They say find a basis for this equation. It's in null space or column space. I promise. Okay. So that is for column space. Null space is a little harder, which sucks, but we deal with it. Yeah.
Give us a question on here that says like, is like 1, 3, 2 in column space? How do you know when the random vector is in column space?
Okay, well, these three are the basis, okay? And I ask, is the vector, let me think. 10, 2, 3, 15. Okay, is this in call of A? But what does it mean for something to be in the column space of A? How else can we say that? Few different things, all of them I heard were correct. To say this is also asking if it's a linear combination, okay? To say this is also asking if we augment it with that vector, is it consistent? Okay, that's how you can check. All right, if it's in the column space, it's consistent, right? That's the definition of what we call column space. It's the span of our vectors, and if something is in that span, it is a consistent vector. Yeah.
Would it augment it with the original matrix?
No, you would augment it with the original. Then oh, that's my bad. You'd augment it here. That's just my fault. Okay, yeah, you augment it with the original thing. Okay. Questions on this? Yeah. Well, yes, you can see that, but that's the same as saying it's consistent. Okay, not everyone has that intuition. And sometimes it's harder to see, much harder to see. Okay, this is the surefire way without having, a very simple matrix and being able to tell quickly. This will always be the way to tell 100% correct. Okay. All right, other questions on this? Yeah. You row reduce it and it's consistent, then it is in the column space. Okay. Anything else on this? Yeah.
Why would you augment it with the original matrix?
He asked, why would we augment it with the original matrix opposed to the row reduced? So an example, what if I give you just the matrix 0, 1? Okay. What does this look like when we row reduce it? Well, it's 1, 0, right? So if I ask, is 0, 1 in call of A? Okay. If we augment it with this one, it's not. It's inconsistent, right? If we augment it with this one, it is. Okay. So you just do A, augment V always. Okay. And then you row reduce. Okay. Does that make sense? This is like here, right? We augment this with the reduced one, it's not true, right? It's inconsistent. Yeah. It's the same thing. The basis is just the columns of A that are important. So you can also augment it with the basis, the same thing. Okay. Don't get too confused on that. If you just want to stick with A, that's totally fine. Okay. Other questions? All right, moving on to basis of null space. Oh, yeah. Okay, sounds good. So just talk about basis of null space. I know it's getting a little late. I'll stick around for a while longer, do some questions and everything. If you need to go, feel free. I don't really care. Basis of null of A. So to find the basis of the null space of A, it is the exact same process as finding a solution set that we've done before. Okay, so we put in reducer echelon form, find parametric vector form, and then these vectors are your basis. Yep, simple as that. Same stuff you did for the first exam, just written a different way. Okay. Questions on that? It's a pretty straightforward process, I feel like, at this point. All right, any other questions on anything I've talked about thus far? Yes.
Can you explain like range between domain?
Yeah, range being it in which context? For onto 101 or all of them?
Yeah.
Okay, so just going back, range is just where we can reach. Okay. So whatever we start with, all of this just gets consolidated into what my range is. Okay, so that's just what it is. It's what happens when I just smush all of this through here and it maps to this. Okay, cool. If you have other questions, I'll be around after too. So, all right, other questions, computation questions, or anything like any kind of question, really. Yeah,
There was a question on last week's video. I don't know if you want to go
Sure.
over it, like,
oh God, which one? This is part of number 2.
any of them. I don't know.
Oh, Jesus. No, I don't, but I'll post a solution to it later because it's work and it would take me a little while to word it all out a second time. I struggled in the studio doing it. Yeah,
Big one.
that's fine.
This is the problem. 3.2.
3.23i. Let me pull it up real quick from the semester, I assume. 3.2 supplement. 3i. Got it.
And 4i, because
3i and 4i. Okay. Okay. Oh, come on. Okay, so let's do 3i real quick. Which of the following transformations are 1-to-1? So this is asking us if this is 1-to-1, okay? Essentially what this is we're constructing a vector here, R2 to R3 defined by this transformation, okay? And we can rewrite this as a vector vertically because that's how I like to see it, right? X minus y, x minus 2y, x plus y, okay? What do we see here? Equations and variables, right? How do we like to write equations and variables in this class? In a matrix, right? So we can rewrite this as 1, -1, 1, -2, 1, 1. And what you'll find is this will row reduce to be 1, 0, 0, 1, 0, 0. And this passes at 1-to-1. Are there 2 pivots or the pivot in every column? Yes. So this is 1-to-1. Likewise, for the second question. That's which of the following we're on to, okay? Same idea. So I'm going to move this right into a matrix. It's going to be x plus y, x plus y. We're going to rewrite this as 1, 1. Oh, no. Got ahead of myself. 1, 1, 1, 1. Okay. This row reduces just to be 1, 1, 0, 0. How many pivots do we have? How many rows do we have? Is there a pivot in every row? Is it on to? Just like that. If it asks you for counter examples where, like, for example, for this one, that it's not in the span, okay? You would just augment it with a B1, B2, row reduce it, and you'll get 1, 1, B1, B1 minus B2. Okay, if they're asking for something that it's inconsistent for, we're solving for anything where these two where this entry is not 0 to make it inconsistent, right? That proves that it's not onto. There's somewhere we can't reach. Okay, so someone give me an example of B1, B2 that it's inconsistent for. 2, 1. What is 2 minus 1? We augment 0, 0, 1. That's inconsistent. Okay. If they ask for something that's 1-to-1, and if you words. If something is not 1-to-1, and they ask for a counterexample of 2 things that map to the same thing, okay? We have a really nice, easy way to get there, right? Because the null space, by definition, are all of my points that map to 0, okay? So all you would do for a counterpoint to 1-to-1, okay? Find the null space, take 2 vectors from it. Because this proves A times what we'll call x1 equals A of x2 equals 0. Because if we pick A1 and x1 and x2 to both be in our null space, A times x1 is 0, and A times x2 is equal to 0. Okay, so that's a good way for the counters of each of those 2 things, if that is asked. Any other questions on this? I know I'm going kind of fast. I want to try to get as much as I can in. Yeah. That's fine. Write a new basis? Okay, that's a really good one. So an example of something that might be true for this is if they give you like a plot, all right, and they say these 2 vectors here and here span this whole plane, right? And they ask for a different basis, okay? How many different bases are there for any given space? Infinite number, right? Because we can pick these two vectors, or we can pick these two vectors, or these two vectors, or any two vectors on this plane that we constructed, right? There's an infinite number of vectors on this plane. So how to find different ones? If they ask for two that are not scalar multiples, okay, all I would do, call it V1, V2 basis. Okay. V1 plus V2 and V1 minus V2 also form a second basis, okay? Or any linear combination of your bases will form another set of bases, okay? So what I mean by that is if they give you three vectors and they ask for a different basis, okay? Just combine those three vectors in unique ways to get three unique different things, okay? For example, like here, I can pick these two, or I can pick these two vectors and stick like this, right? Or I can pick a vector and stick like this, straight down. Or any kind of two vectors pointing in opposite directions, or different directions, rather, that aren't on the same line, okay? Does that make sense?
If you multiply a vector and add them.
Yes, that's fine. Any kind of linear combination is fine. So another example here would be 3v1 plus 2v2, pi v1 minus e v2. Pi and e are just ugly numbers, and this is all I'm trying to illustrate. So these also form a basis. These also form a basis, and this was given to be a basis. Okay. Any other questions on this one? All right, other questions? Yes.
So for problem,
Midterm 1B. Yes, let me get there. Midterm 2A. 2A. 2B. Jesus Christ. Which number was it again? 4A. There was one on here that I thought was a pretty good question that actually took me a minute to solve. And it was asking like which of the following are like in the null space or can you tell aren't. Look over that question at some point. I have no idea what's on the exam. So even if I wanted to hit anything, I have no idea. I can only tell you what I've seen historically. So anyways. Desktop, screenshot. Okay. What this question says, blah, blah, blah. Write a matrix that shows that the null space is the line y equals x. And whose matrix transformation has a range equal to the z-axis. This is a good question. I think this was actually asked on last year's midterm, one of last year's midterms. So we can take this in two parts, either way, all right? So has a range, and we have x, y, okay. Which space does my null space live in? It lives in R to the number of, for null space, R to the number of, that's what it is in R to the number of rows. So then columns for null space. Columns for null space, y'all. So this is number of columns is 2. Okay. Likewise, where does my range, which is my column space, where does it live? R to the number of rows. There we go. So this tells me my matrix is going to have 3 rows. Number of rows equals 3. So I'm going to go ahead and draw 3 rows and 2 columns. Okay. So its range is equal to the z-axis, and it has a null space, right? If it has a null space, what does that tell me about free variables? There are some. What shape is y equals x? It's a line. So how many free variables do we have? 1. The line is dimensional 1, right? So we know from this we have 1 free variable. Okay. And we know what it is. So we can start either with the null space or the column space. Okay. I always choose to start with the column space because I think it is much easier to start from. Okay. If my range is equal to the z-axis, what shape does that mean my vectors take? 0, 0 number, right? The z-axis, yes, 0, 0 and some number, right? To be on the z-axis, that means x and y are both 0, okay? So whatever my columns are, they have to take this shape, 0, 0 number, okay? Someone give me some example of this vector for a first column, because whatever we can do, we can pick a first column and then we can build the rest of the rows from the null space.
0, 0.
1,
1, 0, 1.
no, 0, 0 number.
0, 0, 1.
0, 0, 1. There we go. Totally fine. Okay, so because we wanted to satisfy this, because we want it to be the z-axis. Okay, that's a tricky one. This was actually, I think, the most missed question on this, because a lot of students did start like that. Okay, they just didn't know the shape of it, or they didn't know how to start with the range, or they didn't know how to start with any of that. So we have the first column. Okay, you probably got 70% of the points at this point. All right. Are there any questions on how we got this? Okay, so moving on, null space is the line y equals x, right? But that's not how we like to write our equations for null space, right? How do we like to write them? Parametric vector form, right? Or we can just rewrite that as equation, right? Equal to 0. So let's call it x minus y equals 0, okay? So to reorder this, it's going to be 1, -1, augmented to 0, right? And the rest of my rows, we don't know anything, okay? All null space tells us is what we have an equation for each free variable, and that's it. We don't know what goes beyond that, all right? So each of my rows has to have the form 1, -1. So for example, if my first column, has to have the form 1, the second one -1, okay? So if an entry in my first column is 4, what does the entry in the second column of that same row have to be? -4, okay? So let's look up here. We start with 0. What does the second one have to be? 0. Start with 0, what's the second one? Start with 0, what's the second one? 1. We start with 1, the second is -1. Sorry, y'all. It's been a tough week for me. I'm not gonna lie. It's fine. Grad school is grad school. Don't do it unless you really want to do it. So anyways, so this is an example of a matrix that satisfies this. Okay, there are an infinite number of ways to do this. Okay, because it all depends on how we take our first column and everything else is assigned from there. Okay, so a different example would be is if we picked 0, 0, 4. Okay, if you pick 0, 0, 0, 4, this would still be 0, this would still be 0, this would be -4. Okay, likewise, we can pick -10, 0, 0, -10. Okay, now 0, 0, -10, 0, 0, +10. An equally valid answer. Okay, yeah. Any questions on this one? Oh, that's good. It's kind of hard to read, but that was just getting started. Yeah. Negative here. Oh, for this one. Oh, because in 3D, the z-axis is the x and y is correct, right? Like on a graph, anything that has a positive or negative x or y no longer lies in the z-axis. So just given that it's the range equal to the z-axis, it has to have, every column has to have this one. Okay, so you can double check that to make sure you're right at the very end. Does our second column have this form as well? Yes, right. All right, yeah. How did we know? Well, this is a line in the null space, right? Dimension of a line is 1. Other questions? Yeah. The properties of invertible matrices are all of the properties of onto and all of the properties of 1 to 1. Oh, yeah. So something to note is, like on the last one, you had like multiply 2 matrices, right? This one, you're probably going to have a subpart that is find the inverse. Okay. And what it's going to be is it's going to be a 2 by 2, I hope. And when you do the inverse, it's always exactly the same thing. The 2 by 2 case is the only one that has an easy inverse. Okay. And it is always 1 over AD minus BC times switch A and D and we make B and C negative. Is that right? Somebody correct me. Okay. I always get my letters mixed up. I'm not going to lie. So. Questions on this? So if they give you a matrix, you literally just follow exactly this one. Okay. Make sense? And what happens if this is not 0? Or if this is 0, then what? It's not invertible. We'll learn more about that in the coming weeks, but yeah.
Get the number of rows for range.
The number of rows from range, yes. Yeah. One other note is if for any godforsaken reason, they ask you to take the inverse of a 3 by 3. First of all, I'm sorry. I don't think that's on. That wasn't in any of your PowerPoints, right? Oh, Jesus fucking Christ. Okay. So the way you do this is you take A and you augment it with the identity matrix, okay? And what the identity matrix is it's just 1, 1, 1 on the diagonal, okay? And what you're gonna do is you're gonna row reduce this, okay? And you're gonna row reduce it till you get the identity on the left-hand side. Then whatever is on the right side of the augment bar is A inverse, okay? It is just a headache of row reduction. It is a headache to grade. So for both my sake and yours, I hope it's not on there. And I don't expect it to be. I don't think that was in the coverage of this exam, but you know, just to see it because you'll need to know it going forward. Yeah. Uh-huh. Yeah. Say that again. What do you mean quantity? Like AB squared or? So they have A. Like.
Yeah.
Oh, okay. And what about it? No. So something that's different about linear algebra is we cannot multiply 1 times 2 the same. We can multiply 2 by 1. They're different things. Okay. A times B and B times A are different values. Okay. So it's called left multiplying and right multiplying. So this is A plus B times A plus B. Okay. So we FOIL first outside and inside last. A squared plus AB plus BA plus B squared. A, B, and B are not necessarily the same. So this is as simple as we can get it. There's no combining this middle term. And okay. Matrices are annoying, but this is one of the things we do. Okay. You can think of it as doing it as order of transformation. That's another thing you guys should really know how to do, is how to, they ask you a transformation, you can put it in a matrix. Okay. Yeah.
Like is A like a power or something convertible? Is A convertible?
Yep, it is. Yeah, because think of it if you do something once, okay, and you can undo it. Okay, if you do something 16 times, you can still undo it, right? But as soon as you do something you can't undo, you can never go back, right? I'll do maybe one more question. Yeah. Linear dependence and independence. Let me do a computation question and then I'll answer that after the fact, okay? Any questions? Did you have? No. Yeah.
There was a question where it said A plus B for the whole thing inverse.
Yeah.
It says equal to A inverse plus B inverse. It's false.
That's false.
Is there like a reason?
Multiplication and addition are not inverses of themselves. Okay, that's just a little sidebar. Yes. Rank theorem?
Yeah.
Is that the rank nullity theorem?
Yeah.
Okay, rank nullity theorem is it's very lovely in that it's very concise in its name. Okay, so the rank nullity theorem is rank plus nullity equals number of variables. Okay, so rank is our dimension of our column space of A, and nullity is our dimension of our null space of A is equal to number of variables. Okay, what's the dimension of the column space of A? It's our number of pivots. What's the dimension of our null space of A? Number of. How else can we say number of variables in terms of a matrix? Number of columns. X's are also fine. Number of columns. Okay, so this is just saying every pivot column, number of pivot columns plus number of non-pivot columns are number of columns. Does that make sense? Yeah. That's the whole definition of it. Yes. What? I am good for one. I was waiting for one. Practice A. Okay. Same midterm 2A. The number 2. Any part in particular? A and D. Okay. Okay. 803. Come on. Okay. So this question asks for subspace stuff, all right? Given A and B are in R2, given two variables, is A times B equals 0 subspace? They're multiplied together. Is anything multiplied together in subspace? No. Yeah. Okay. That's just a rule of thumb, a way to check this. Okay. 0, 1 and 1, 0, right? Both satisfy the condition, right? When we add them together, they give 1, 1, right? Does 1, 1 satisfy the condition? No. Okay. The second one, is this a subspace? Yes or no? Why?
A minus B equals 0.
Yes, we can rewrite this as A minus B equals 0. And what do we call something that's in this form? A null space. Null space is a subspace. Okay. Likewise, another example is if they give you X, Y, and Z, and they ask, is X plus 2Y, 3Z, 2Y plus X. Oh, that's the same thing, second time. They ask, is something like this a subspace? Yes or no? Why? Different answer. Easier answer. Is the column space. Right, this is the same thing as this is how they would write like the column space and try to trick you. This is how they would write a null space and try to trick you. Okay, yeah.
If you can put it in a matrix, that means it's a subspace?
Yes. Concrete answer, yes.
Right.
And a good thing to note is, can you, like a +1, can you put that anywhere in a matrix? Can you put X times Y anywhere in a matrix? No. So but a little side note I'll say, same thing with like the squares and rectangle stuff. Just because we can't put it in a matrix doesn't mean it's not a subspace, okay? It just means we have to be a little bit more careful. All right? Yeah. No, I'm about to. Oh, look, there's the thing I was just talking about. Let W be the subspace of R3 in the form A, B, A minus B, where A and B are real numbers. Is this a subspace, yes or no? Why? This is just a column space. We can rewrite this as 1, 0, 0, 1, 1, -1, right? Where my first column is A, my second column is B. Each equation is each row. So we put it in a matrix, therefore it's a subspace. One very tricky place you have to be careful. This number might be different. Is this a subspace of R3? It's a column space, subspace of R3. But we have 3 rows, so it's a subspace of R. No, that was the number. Okay. Any other questions on 2A? So again, the way we can tell is just because they give us vectors like this that are constructed from inputs, which is just the definition of columns. Okay. Cool. Okay. Moving on to 2D. 2D. Suppose A is a 3x4 matrix in the parametric vector form, and the solution is blah, blah, blah. So 3x4. 3x4. What does this parametric vector form tell me? X3 is a free variable. Okay. So yeah, have a good night, y'all. So we have how else we can say this is we have pivot, free variable, pivot. Okay. So how many pivots do we have? What's the shape of my column space? How many pivots do we have? 3 in, how many rows do we have? 3, right? So this is all R3, right? And we can tell that by going from this number of free variables in the shape they tell us. We can tell the number of pivots. We can tell the number of pivots. We can tell the shape of both the null and columns. Okay. So this person says A equals B is consistent for every B in R3. What's another way to ask that question? Pivot in every row. What else do we call something that's a pivot in every row? Onto. That's what this question is asking. Is this matrix onto? How many pivots do we need for it to be onto? How many do we have? It's onto. Okay. If B is a vector in the column space of A, the set of solutions to AX equals B is a line in R4. True or false? Why? I was gonna say why, it said yes or no, so I didn't mean to put you on the spot. Oh, this is a line. I thought, okay. I read this question wrong. I'm not gonna lie. Okay. Vector in the column space, the solution is a line. That is true because we have one free variable. I thought it mentioned the origin, which is not true because it'd be a shifted line. Okay. But a line is a line is a line. Okay. So this one is true. Let me double check their solutions, just quadruple check myself. Yeah, this is true, right? Because any solution is going to have span of 1, 1, 1, 0 plus V particular. Okay. So it's always going to be a line shifted by some amount. Okay. Well, if B is 0, what is our particular solution? Oh, if B is a line, Jesus Christ. I'm so sorry. If B is 0, what is V particular? 0, right? This is 0 if and only if we're solving a homogeneous system, which means it's equal to 0, which means a null space, we just have this, no particulars. Okay. All right. So D3, the first 3 columns form a basis, true or false? Why? The third one is not a pivot. Which 3 columns do form a basis? First 2 and the fourth. Yep. That's no. Any other questions on any of this? All right, cool. I'll hang out for a few more minutes for any other additional questions. And yeah, good luck on the exam. If you're in my section or section A, I'll see you during the exam. So yeah, good luck, y'all.